Hello class 12 science. Today we are going to start the second chapter of inorganic chemistry, and the chapter name is coordination compounds. In this chapter we are going to study about important terms related with the coordination compounds, and then after that naming of coordination compounds, and lastly isomerism of coordination compounds. So first we'll begin with the difference between the double salt and complex compounds. Double salt means those molecular compounds which exist only in crystal lattices but break down into their constituent compounds when dissolved in water or any other solvent is called double salt. For example, more salt is written as FeSO4.NH4 twice SO4 6S2. In this we have got the mixture of two salts. One is ferrous sulfate and other is ammonium sulfate. So it is an example of double salt. So this salt, when dissolved in water, they break down into their constituent compounds, okay, as well as potash K2SO4 K2SO4 Al2SO4 thrice 24H2O. These are the example of double salt. Now coordination compound or complex compound means those molecular compounds which retain their identities even when dissolved in water or any other solvent, and their properties are completely different from those of the constituents. So coordination compounds or complex compounds are the compounds which retain their identities even when dissolved in water, and their constituents will be completely different from their complex compounds, we can say. Example, cobalt NH3 6Cl3. Okay. This is an example of a coordination compound. And K4FeCN6, this is potassium hexacyanoferrate. Okay. So this is the definition of coordination compounds or complex compounds. So we are basically in this chapter we are going to study about such kind of compounds. Now important terms related in the coordination compound. One is central metal atom or ion. The metal atom or ion to which certain atoms or groups of atoms are permanently attached in a coordination compound is known as central metal atom or ion. So for example, in K3FeCN6, so in this compound the central metal atom, okay, is Fe, okay, and the valency of that will be 3 plus, so it is known as a central metal ion. Ligand means this, the groups that is attached to the central metal atom. A ligand is a species that is capable of donating an electron pair or pairs to a central atom or metal ion, okay. So they are called as ligands, and ligands are classified upon the number of coordination sites or the number of electron pairs they donate. Say for example, monodentate ligand donate only one electron pair. Example, ammonia NH3, they've got one lone pair of electron. Phosphine PS3, similarly H2O. Okay. So all these are monodentate ligand which has got one donating site, we can say. Similarly, bidentate ligand means they possess two donor atoms and can form two coordinate bonds. Example, oxalate ion. So in this oxalate ion, this O is also negative and this O is also, so both of them can donate a lone pair of electron. Similarly, in ethylene diamine, this compound is ethylene diamine, where NH2 and NH2, the nitrogen has got the donor electron, or dimethyl glyoxime. Similarly, tridentate ligand will have 3 donor atoms, okay. So the example is diethylene triamine, this compounds where we have got 3 nitrogen with a lone pair of electron. Similarly, tetradentate have got 4 and they will have 4 donor atoms. Pentadentate, they have got 5 donor atoms. Hexadentate 6, okay, like that. Next we have got a bridging ligand. Bridging ligand means the monodentate ligands which can be simultaneously attach themselves to more than one metal atom. So the monodentate ligand which can attach to more than one metal atom simultaneously, they are known as bridging ligands. Next, ligands can also be classified on the nature of the charge. Say for example, if they do not contain any charge, they are called as neutral ligand. Example, H2O, ammonia, carbonyl, nitrosyl, all these are neutral ligands, they don't have charge. Anionic ligand means they carry negative charge, like F minus, Cl minus, Br minus, Cn minus, OH minus, acetate ion having a negative charge. They are called as anionic ligand. Cationic ligand means they are having positive charge, like NO plus, that is nitrosonium ion, NH3 NH2 plus, that is hydrogenium ion, and NO2 plus nitronium ion. Okay, so they can also be classified on the basis of their types of ligands. Next we have got a topic known as chelation or denticity. Okay. Now chelation or denticity means some ligands are capable of donating more than a single electron pair from different atoms in the ligand and to form different sites in the geometric structure of a complex. Okay. These are called multidentate ligand. Now, when the bonding of multidentate ligand to a metal ion produces a ring, usually 5 or 6 membered, we refer to the complex as a chelate, and this process is known as chelation. Now, in this, you can see that this copper and this is dimethylene diamine. So over here, these two donor atoms have donating electron to the copper atom, and so they are forming a coordinate bond. Now, if you see this, they have formed 5 membered rings. So if they form a ring like a structure, they call as chelate, and the process of formation is known as chelation. Okay. Next we have got ambidented ligand. The monodentate ligands which can coordinate with the central atom through more than one site are called ambidentate ligands. So the monodentate ligands which can coordinate with the central atom through more than one donor site, they are called as ambidentate ligand. Nitro. So in this nitro, the nitrogen form a coordinate bond with the metal, and with the same monodentate ligand, oxygen can also donate electron to the metal. So this will be nitrites and nitro. So in this, the same molecule, we can have a 2 donor atom. Such kind of ligands we call ambidentate ligand. Next, coordination entity or complex ion, what it is called. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of oppositely charged ions or neutral molecules. It also represents coordination sphere. This type of complex behave as one unit and is ionizable. Say for example, if you write this coordination compound, so whatever there is in the square bracket, that will be called as coordination entity. Okay, so coordination entity can be a positive, it can have positive charge, it can be negative, or it can be neutral. So positively charged examples are shown over here, a negatively charged over here, and this is the neutral where they don't have any charge. Okay, so based on their charges they can be classified. Next is coordination number. Coordination number means the total number of coordinate bond formed with the central metal atom or ion by the ligand, or in other words, we can also define as the total number of ligands attached to a central metal ion is called the coordination number of that ion. Say for example, in this AgCN2, the number of ligands attached to silver is 2, so the coordination number of silver will be 2. Similarly, in this cobalt is attached with 3 ammonia and 3 chlorine, so altogether we have got 6, so the coordination number of cobalt will be 6, like that. Okay. Next, oxidation number or state of the central metal atom. How to find? Say for example, the oxidation number of iron in this compound, potassium hexocyanoferrate. Okay, so you need to find the oxidation state of iron, Fe. So for that, what you can do is potassium having a positive charge, 1 positive, will multiplied by 4 into oxidation number of K plus, because we have got 4 potassium. Oxidation of iron we don't know, so we need to find it out, plus CN6. So cyanide, we have got 6 cyanide, and Cn has got a negative charge 1. So altogether potassium has got 1 positive charge and minus 6. So when you just simplify it, you'll get the oxidation number of iron as plus 2. In a similar way you can find for other as well. Next, coordination compound. This is the simple summary that we have learned important terms. So this is the coordination compound. In this we call it central metal atom or ion. These two are called ligands. This is a coordination pair, or we can call coordination entity, and coordination number of this will be 2 plus 4 plus 2, that is total number of ligands 6. Okay, and this will be the ionizable or counter ion, we can say. Next is Werner theory of coordination compound. According to this theory, it tells us there are two types of valences shown by central metal atom or ion in a compound. One is primary valency and other is secondary. The primary valency is ionizable, whereas the secondary valency is non-ionizable. Primary valency corresponds to oxidation number and secondary valency corresponds to coordination number. So in the complex, this complex, primary valency of cobalt is 3 and secondary valency is 6. Okay. Next, primary valency is satisfied by negative ions or anions, while secondary valency is satisfied by ligand. So primary valency is satisfied by negative ions, whatever negative ions are there, and secondary valency by the number of ligands, which can be neutral, positive or negative. Next, every metal atom has a fixed number of secondary valences, that is, it has a fixed coordination number. The secondary valences are directional and are responsible for definite geometry and isomerism of the coordination compounds. Next, primary valency in the complex is represented by a dotted line, while secondary valency by thick line. This we can see later on with the structure. In all cases, metal or metal ions should satisfy both primary and secondary valencies. Next, a very important part of this topic, of this chapter, nomenclature, or writing the IPAC name of the coordination compounds. What are the different rules, how to write? So first is ordering of naming ions. In ionic complex, the positive ion, that is cation, is named first, followed by the name of negative ion and ion. Say for example, in this K3FeCN6, the first potassium is named as potassium hexacyanoferrate. Okay, so the first positive part is named first, then negative one. Naming of the coordination entity. In naming the coordination entity, the number and the names of ligand are written first, followed by the same of the central metal atom or ion. The metal atom as well as the ligand are written without any space between them. Sorry, I'll read it just once more. Naming of the coordination entity. In naming the coordination entity, the number and the name of ligands are written first, followed by the name of the central metal ion. Okay, so when you write, so the first, the number and the name of the ligands are written first. Okay, then after that, central metal ion. The oxidation number of central metal ion is represented by Roman numerical. You would write down the oxidation state in Roman number. The metal atom as well as ligand are written without any space between them. Okay, and naming of ligands. Say for example, if you have got an ionic ligand, so it will end with O. In general, if the anionic name of the anionic ligand ends ID, E, IT or AT, the final E is replaced by O, giving iodo, A2. Okay, so for example, Cl minus is written as chlorido, NS2 minus amide, okay, like that. So if you have got sulfate, sulfato, okay, cyanide, cyano, cyanido, like that. And if I have got a positive ligand, it will end with IUM. So for NO plus nitrosonium, NO2 plus nitronium, like that. Similarly, neutral ligands, these are ethylene diamine is written ethane 1,2-diamine, pyridine, triphenyl phosphine, like that. And if you have got neutral ligands like water, it is written as aqua, NH3 amine, NO nitrosyl, CO carbonyl, right? In a similar way, you can just go through this rule from your textbook as well. What are the rules? And after that, I'm coming how to write, because rules, how to apply the rules over here. Say for example, we have taken this compound and you are asked to write down the code name for this. The structure is this one: CuH2O2 NH3 SO4. What will be the name for this? So the first thing is written this one, whatever is in the coordination pair. And in this also, first we'll write down the ligands. These are the ligands. We have got H2O and NH3. H2 is written as aqua and NH3 is written as amine. So both are starting with A, so we'll follow the alphabetical order which we are going to write first. Aqua, AQ, this is amine, AM, so amine will come first. And since over here we have got 4, the name will be tetra. Tetra, this is amine. Okay, and there over here we have got aqua as 2, so diaqua. This metal copper, and the valency is 2. Why? Because SO4 is written 2 minus, so overall charge will be 2 plus. And since these are neutral to neutral, so 2 plus will be the charge for this copper, so 2 sulfate. So this is the IPS name for this compound. Similarly, one more example. In this also, in a similar way, we have got amine and sulfato, since it is written is over here. So amine will come first, so 4 tetramine, sulfate, sulfato only 1, sulfato, this cobalt, the valency of this will be 3, cause this will be -1 and this will be +1. So in order to +1 with this would be 3, because sulfate will have -2. So call it cobalt 3 nitrate. This is how we'll write on the IPS name. Okay, this is for your practice. Okay, you can write down the coordination name for this, IPS name for this. Next, the topic is of this coordination compound is isomerism. Okay, isomerism. Isomerism in coordination compounds is generally classified in 2 types: structural and stereoisomerism. In structural, we have got ionization, hydrated coordination, and linkage isomerism, and in this we have got geometrical and optical isomerism. So in structural isomerism, this type of isomerism arises due to difference in structure of coordination compounds. They are of following types. Number 1, ionization energy. Okay, so in ionization isomerism, what will happen? The compounds having same molecular formula but give different ions in solutions are called ionization isomers. Okay, it exists due to an exchange of groups between coordination and ionic space. Say for example, this compound CuNH3,5Br(SO4) and this is CnH3,5SO4Br. If you see these two compounds, the only difference is that in this Br is inside and sulfate is outside. In this sulfate is inside and Br is outside. So exchange of ions, we can say. Such kind of isomerism is called ionization isomerism. Next is solvate or hydrated isomerism. Hydrated isomers are isomers of a complex that differs in the placement of water molecules in the complex. For example, CrH2,6Cl3. This will be a violet color, anhydrous. Okay. And if you just place this one Cl inside the coordination sphere and one water out, it will be a light green, monohydrated, like that. If you put 2 Cl inside and take out one more H2O, it becomes dark green. So they are called as hydrated isomerism, water isomerism. Next is coordination isomerism. In coordination isomerism, when both the positive and negative ions are complex ion, isomerism may be caused by the interchange of ligands between the anion and cation. They are called as coordination isomerism. This arises only if cationic and anionic metals have same coordination number and charge. So for example, so this is the example of coordination isomerism. So if you see over here, CuNH36, CrCN6. In this CrNH36 and CuNCN6, what has happened over here? This NH3 has gone over here and CN6 over here. Okay, so coordination isomerism. And the last fourth type of structural isomerism is linkage or structural salt isomerism. This type of isomerism arises when the ligand may attach to the central metal ion of a complex in different ways, that is of ambidented ligand. So for example, in this, if you see, this is pentamine nitro cobalt chloride, which is red in color, and in this it is pentamine nitrito cobalt chloride, which is yellow brown. Now you'll see the difference over here. It is nitro NO2, this ONO. Okay, so one is nitro and other is nitrito. This example we have seen in the case of ambidented ligand. Such kind of isomerism is called linkage isomerism. Finally, geometrical isomerism. Geometrical isomerism. This isomerism is due to ligands occupy different position around the central metal atom or ion. When the ligands occupy adjacent position are termed as cis form, and when the ligands occupy opposite positions are termed as transform. This type of isomerism is not shown by compounds having coordination number 2, 3, 4. This isomerism is very common in square planar and octahedral. Now, to understand geometrical isomerism, it has got cis and transform that we have a previous knowledge in class 11 as well. In cis and transform, what will happen? Say for example, if this is a central metal ion, and if you have got the two similar groups on the same side, then it is a cis form. Cis means same. And if you have got the two similar groups on the opposite side, then it is a transform. Say for example, in the example over here, we can see that this is a platinum. We have got ammonia and chlorine, and here we have got py is pyridine. So these two groups are on the same side, so cis form. And the group py and py, that is pyridine, they are opposite, so it is a transform. Now assignment for today, assignment 15. Question number 1, differentiate between double salt and complex compounds. Question number 2, explain with examples each of the following: coordination entity, coordination number, and ligands. Question number 3, write IPAC name of the following. So please write down the IPAC name of these compounds, okay, of these 4 compounds. After that, question number 4 is write the formula of the following coordination compounds. Now from this name you need to write down the formula as this one, like this, okay. Tetramine diaqua copper 2 sulfate and hexamine cobalt 3 chloride, okay. Question number 5 is draw the geometrical isomerism exhibited by the compound platinum PtCl2 NH3 twice. And question number 6 is name the types of isomerism shown by the following periods of compound, these compounds. So CuNH3 5Br SO4, CuNH3 5 SO4 Br. So you need to write down what type of isomerism they are showing. And this one is, second one is COCl H2O NH3 4 Cl2, COCl2 H2O NH3 4 Cl H2O. So what type of isomerism? So complete this assignment and send it in my mail.